Welcome to another VMware Secrets Manager use case demo. In this demo, we will federate two Kubernetes clusters and share secrets between these clusters. This way, you can securely share your secrets between workloads, independent of where they are. For example, you can have a server application on an Amazon EKS cluster, a client application on an Azure AKS cluster, and, let's say, an analytics application on a bare metal Kubernetes cluster on your data center. By federating these clusters, and with the help of SPIFFE and SPIRE, and VMware Secrets Manager, you can distribute secrets from a central secrets store to these workloads that reside in different cloud providers. Before we begin, here's the topology we will use in this demo. We'll have vSecOps Sentinel and our demo workload in a cluster named Cluster 1 Demo, and we'll have vSecOps Safe in a different cluster, Cluster 2 Demo. We will establish a federation relationship between these two clusters by using what's called a cluster federated trust domain abstraction. Once the clusters are federated, the workloads and vSecOps Safe interaction will be as if they are on a single unified cluster. The cross-cluster MTLS connectivity and trust relationship will be established by SPIFFE. The YAML manifests in this demo are slightly modified versions of the default Secrets Manager deployment. I'll review the YAML manifest files and tell you what has changed to establish the cross-cluster federation. Also, you can find the source code of this demo at this link. We'll start with the SPIRE server's YAML manifest. The first thing that has changed is this trust domain. Our trust domain is this cluster, which we identify as Cluster 1 Demo. We have a bundle endpoint that we expose to establish a federation relationship with the other cluster. Cluster 2 Demo in our case, we are federating with the Cluster 2 Demo trust domain on this bundle endpoint, which means we'll expose this service on Cluster 2, and we'll expose this service on Cluster 1. To ensure these endpoints have network connectivity, since this is a bare metal setup, we'll use MetalLB as a load balancer to be able to assign these endpoints unique IP addresses. Also, note that Cluster 2's bundle endpoint's SPIFFE ID is Cluster 2 Demo/Spire/server. The rest of the configuration is a default Spire setup. I haven't changed anything related to federation there. Now, let's check the Spire agent setup on this Cluster 1 Demo. Again, in the agent conf, we have changed the trust domain to Cluster 1 Demo. The Kubernetes Projected Service Account Token, PSAT, attester, will request the cluster name to be Cluster 1 to trust the Spire server. We have also declared on the Spire servers, Kates_PSAT, configuration, a matching stanza like this. Again, the rest of the configuration is in its default setting. Now, let's look at what we have in Cluster 2. Again, I'll start with the Spire server. We name the trust domain Cluster 2 Demo. We are federating with the Cluster 1 Demo trust domain that exposes its bundles at this address using this SPIFFE ID. We have a Kates_PSAT node attester, defined for the Cluster 2 cluster, and I've left the rest of the server configuration intact. The agent configuration will also have similar changes to what we did in Cluster 1. Let's check them out. Our trust domain is Cluster 2 Demo. The PSAT node attester will assume the name Cluster 2, and I've left the rest of the file intact again. Let's apply these changes. In this demo setup, I've split this terminal into 4 quadrants. The top left is where I'll enter commands for Cluster 1 Demo cluster. The bottom left will be where I'll tail the logs of the Spire server on Cluster 1 Demo cluster. The top right is where I'll enter commands for Cluster 2 Demo cluster. And bottom right will be where I'll tail the logs of Spire server for Cluster 2 Demo. To be clear, the screen's left and right half are connected to 2 different machines, with 2 different IPs, with a single node Kubernetes cluster on each of the machines. There is network connectivity between these 2 machines. Again, you can get the source code of this demo from the link you see on the screen. The first thing we'll do is to establish a federation relationship between these 2 clusters. To do this, we'll use the cluster federated trust domain abstraction. But first, I'll create a SPIRE system namespace, as all of the SPIRE-related components will be put into this namespace. kubectl create ns, SPIRE system, and it's done. I'll do the same in the other cluster. Essentially, these two clusters' SPIRE setups will mostly mirror each other. kubectl create ns, SPIRE system, and it's created too. Then I'll go to the SPIRE folder and do a kubectl apply-k to deploy two SPIRE installations in these two machines, based on the configuration parameters we've seen before. Let's verify the status of our SPIRE installations. kubectl get po-and SPIRE system. We have a healthy SPIRE installation with the SPIRE server and SPIRE agent up and running. When I kubectl get po-and SPIRE system in the other cluster, I get a similar outcome too. Now, I'll copy the names of these SPIRE server pods and tail their logs here to observe what's happening behind the scenes when we register SVIDs to the system, query the workload API, and federate clusters. Let's tail them with kubectl logs pod name-f here. Let's do the same here too. Perfect. For these SPIRE servers to federate with each other, they need to have bundle endpoints that they can access over the wire. To achieve that, I'll create this service of type load balancer in both machines. Switch to the bundle folder in both of the machines. Then kubectl apply-f endpoint.yaml in both machines. Now, let's list service endpoints in the clusters for the SPIRE system namespace. kubectl get service-an, SPIRE system, and we have a bundle endpoint serving at a cluster IP in the cluster 2 demo cluster. Let's do the same for cluster 1 demo. kubectl get service-an, SPIRE system, and we have a service with a cluster IP for the bundle endpoint here too. Now, let's telnet these endpoints to verify network connectivity. On cluster 1 demo, telnet 10.0.0.70.8443. And on cluster 2 demo, telnet 10.0.0.150.8443. We verify that we can open connections to both bundle endpoints. Note that these IPs may differ depending on your ingress configuration. In this setup, we used metal-LB to assign IP addresses to services within the IP range 10.0.0.150 and 10.0.0.160 in cluster 1, and 10.0.0.70 to 10.0.0.80 in cluster 2. Now, we can federate these clusters, and for that, we'll use cluster federated trust domain constructs, but we still need to extract the trust bundles from the servers for an initial handshake. And for that, we have a script. On the SPIRE server pod, we execute SPIRE server bundle show -format SPIFFE, giving us the trust bundle of whichever server we run this command on. So let's execute this print bundle script in both of the servers, and we can see the bundles of both of the servers. To establish trust, I'll need to enter the bundle of cluster 1 to cluster 2, and set the bundle of cluster 2 to cluster 1 in the corresponding cluster federated trust domain manifests. I'll copy these JSONs and paste them onto a text editor, then paste the bundle of cluster 1 to the manifest of cluster 2, and vice versa. When I save, and kubectl apply-f for both manifests, SPIRE Controller Manager will do the hard work and exchange these bundles between SPIRE servers to establish a federation relationship. And you can see in the logs that the federation is established in both servers. Next up, as per our diagram, we'll install Sentinel to cluster 1 demo, cd Sentinel, and for Sentinel, we have a service account, a cluster SPIFFE ID that is designed to federate with cluster 2 demo, because we'll have vsecm safe there, so it needs to talk to that cluster. A SPIFFE ID that is under the cluster 1 demo trust domain, and a vsecm Sentinel deployment with slight configuration tweaks that deviate from the default setup. First of all, the workloads will have cluster 1 demo/workload prefix, because our workloads will be in this cluster 1 demo to receive secrets. Secondly, Sentinel will have a cluster 1 demo prefix too, because Sentinel is in the same cluster as the workloads. We could have split it into a different, more secure cluster, and may have established a three-way federation, But for the sake of simplicity, we'll keep Sentinel in the same cluster as the workloads. The safe SVID prefix will point to cluster 2, because vSecum safe resides in cluster 2 demo. Let's first assign a cluster SPIFFE ID to vSecum Sentinel by kubectl apply-f identity.yaml. Then, once we get and describe the cluster SPIFFE ID, we'll see that no pods match. Because, well, we haven't deployed any pods yet. Let's deploy the vSecum Sentinel pod too. But before that, let's create a namespace first. Kubectl apply-f namespace.yaml will create a vSecum system namespace. Then apply a service account. Kubectl apply-f service account.yaml. And finally, install the vSecum Sentinel deployment using kubectl apply-f deployment.yaml. When we kubectl get po vSecum system, we see a healthy vSecum Sentinel pod there. That's good. When we describe the cluster SPIFFE ID of vSecum Sentinel, we see one pod selected, which means our vSecum Sentinel can retrieve SVIDs from the SPIFFE workload API. When I execute safe-h in the vSecum Sentinel pod, I see that it responds to my command and displays a descriptive CLI help message, which shows that the pod is healthy. Now, let's go to the second cluster, cluster 2 demo, and deploy vSecum safe there. The cluster SPIFFE ID of vSecum safe will be similar to Sentinel's, but instead of cluster 2, it will federate with cluster 1 demo. Its SPIFFE ID template will start with cluster 2 demo because our workload resides in cluster 2. The rest of the ID is pretty much standard. I also copied cluster role and cluster role binding from the default vSecum safe installation manifests. I won't change them and apply them as they are. We need to expose vSecum safe as a service for vSecum Sentinel in the other cluster to register its secrets over MTLS, and this is the manifest for it. Again, we'll leverage MetalLB since this is a bare metal cluster. MetalLB will help us use a service of type load balancer. We'll have an associated service account for vSecum safe too. Let's apply all of these and see what happens. Kubectl apply-f namespace.yaml, kubectl apply-f identity.yaml, kubectl apply-f role.yaml, kubectl apply-f secret.yaml, kubectl apply-f service account.yaml, kubectl apply-f service.yaml. When I run a kubectl get cluster SPIFFE ID vSecum safe and then describe it, we see no matching paths as expected. Let's do a kubectl apply-f deployment.yaml to install the pod for the cluster SPIFFE ID to match. And when we describe cluster SPIFFE ID vSecum safe again, we now have a matching pod, which means vSecum safe can receive an SVID from the SPIFFE workload API, and that means it can establish MTLS connectivity with cluster 1 demo. Let's check the vSecum safe pod. Kubectl get po-n vSecum system, and here it is. And I'll print its logs here too. As you see, vSecum safe has bootstrapped successfully and is ready to serve. Let's check the service endpoint of vSecum safe. Kubectl get service-n vSecum system. This is our IP for vSecum safe, which is externally accessible. Let's test the connectivity. Telnet 10.0.0.71 at port 8443, and we successfully established a connection. Let's establish an actual command and verify the cross-cluster interaction works. We'll run safe-l on the Sentinel pod. We get an empty JSON because we haven't registered any secrets yet, but this proves that we could query vSecum safe via a cross-cluster MTLS REST API. Now, let's register a secret using this command. And we got an OK, which means we successfully registered the secret to the example workload. And when I list it, I can see it. OK. Now let's deploy an inspector workload to ensure that the secret can be delivered. This is the cluster SPIFFE ID of our inspector workload. Cluster 1 demo is our trust domain, and we are federating with cluster 2 demo to fetch secrets from vSecum safe through MTLS. This is a typical service account, nothing fancy. And this is our deployment. Again, there are slight modifications through environment variables to tell the workload that vSecum safe is in cluster 2, and the workload will be assuming a cluster 1 demo trust domain, and the vSecum safe endpoint is this IP, instead of the in-cluster DNS name that vSecum assigns by default. So, let's apply these. kubectl apply -f identity.yaml, and then when we get and describe cluster SPIFFE ID, there are no matching paths as expected, because we haven't deployed any yet. Let's apply service account, deployment, and then kubectl get po, and we have this inspector pod here. Let's assign a variable for this pod name. When we execute the env command in this gadget pod, we see the secret that we set displayed on its console. Let's tail vSecum safe logs and try this command again to show that we are actually hitting vSecum safe. When we run the env command, we see that the request reaches vSecum safe, and safe displays some audit logs on its standard output. Or if we list secrets like this, you can again see audit logs on vSecum safe here. That finalizes our demo, where we delivered secrets to workloads across clusters using SPIFFE, SPIRE, and VMware Secrets Manager. Until next time, keep your secrets secret.